Okay. So, what we have is your P C r is equal to pi square E I by L square is 1. So, if I write this in terms of stress, sigma C r is equal to pi square E by L by r whole square, and this L by r we call it as slenderness ratio, that is pi square E by lambda square. I can write anyway. Okay. So, provided your system follows the Euler principle, right, that is very important. That means the column must follow Euler's principle. Okay. So, I will just continue a little bit of that. What is meaning that? That means I told you this PCR, I mean this sigma CR, the stress is less than your sigma y yield stress, right, very very important. This Euler principle or Euler theorem works only when this stress sigma CR, this PCR works only when sigma CR is less than sigma y. If it is less than more than sigma y, will not work. Okay. That means your first yielding is taking place. If yielding takes place after the buckling takes or not, does not matter, right. So, then at this stage we call it as crushing. If sigma y is more than sigma CR, we call column to be crushed. Column to be column crushed. So, yielding took place, right. After that, if buckling takes place, what is use of that? We do not know. Whether anyway column failed, after failing the crushing, whether the buckles or what happens does not matter, is it not? So, you understand, right. So, that is what very important to understand. So, what does this mean? That I have to find out sigma CR, and I also have to find out the stress sigma y, which is nothing but your P by A, area of cross section. How much P is coming? P load coming divided by area of cross section. So, this stress, if it is less than, if this stress is, if it is more than the sigma CR, then your buckling starts. If right, very very important. I hope this is clear, right. Two things you have to compare, sigma CR or sigma y. Means these are both capacities. Sigma y is a crushing capacity or yielding capacity. So, both are capacities. So, this is buckling capacity, this is crushing capacity. Whichever early happens, that fail, but we know this is going to happen early. The sigmas here expected to happen early. That is what the important assumption in your Euler's theorem. Right? If this happens early, then your theorem will not work. This theorem will not work. Euler's theorem will not work. Please pay attention to this. Okay. So, then I just want to move on to the next concept, something called efficient column. Efficient column, right. What is efficient column? That means we are looking for a cross section of the column, So, if you look at now, suppose I take a rectangle, column here. I will just write down one rectangle column. I am drawing in the cross section. So, these are all plans cross section. I take a square column, right. I take a circular section solid, I take a pipe section, something like this, right. Now, as we learned that if this vertical axis is your, let us say, A axis, and this is your BB axis, common for all, BB common for all, this is solid, this is full solid BB, and this is AA we know AA equal to BB in both cases, AA equal to BB, right, and because this is a symmetric, this is A BB. Now, my point is only if I want to find out the PCR, what I am going to do, pi square EI by L square, right. Now, what will be my I is very important decision factor for the column buckling. So, this I will be your least momentum inertia. Now, look at this particular plan, the first case, let us say this is A case, B case, C case and D case, right. We have a 4 cases, right. So, for A case, what is IA? IA, so let us say this is my thickness T and this is the width D, right. IA will be D T q by 12. Now, IB will be your T D q by 12. So, definitely IA is much smaller than IB, that means IA is the least. So, it is going to fail with respect to axis AA, right. Instead of A I can call it as X, instead of B I can call Y. So, IX or IY we used to call. So, now I think another axis A. So, I have to write here as IA, very important. Now, coming to the same for the case of B, case B, for a case B. So, what is IA? Because both sides same dimension. So, D into D cube. So, D power 4 by 12, right, D power 4 by 12. So, same thing will be your IB, right, this will be your IB. So, either side it is the section is stronger. So, now PCR will be pi square E I A or B by L square, equally strong both. For C case, I A is your what? Pi by 64 D power 4, right. Now, for D, what is that? I A, this is also equal to I B. So, here pi by 64 capital D power 4 minus small d power 4. So, these are the momentum inertia which is also equal to I B. So, my point here to drive to you is that you choose a column which is I A equal to I B, or generally what we call, or I X equal to I Y. That is how you should choose a column. So, to have I X equal to I Y, you better choose a, let us say, hollow section, complete solid square, it means dimension, let us say D, and this will be D, or you choose solid circular, which is again solid and same, right, you got I X equal to I Y, or you can choose which is hollow or hollow circular. Now, I want to, this is one. So, in all the 4 cases, like case A, case B, case C and case C, in all these cases you have I A equal to I B or I X equal to I Y. Now, among these 4 cases, which case will be my efficient further? Because you understood one case, understood efficient column is that column where I X equal to I Y, okay, or I A equal to I B, whatever that momentum inertia with respect to one axis should be equal to another axis, one efficiency. Second efficiency will be the material. If I draw the x y axis and x axis, right, let us say this x axis or y axis or a axis or b axis, it does not matter, then the material around the centroid is going to be wasted. The material around the centroid will be wasted. So, if the area which is away from centroid will contribute more in your momentum inertia, that is going to be very efficient section. So, comparing to the A, B, C, D, so C and D will be efficient. C and D will be efficient because I am wasting a material which are near centroid. Near centroid, material is going to be wasted. Is not going to contribute to the moment of inertia much. We know that, right? What is moment of inertia? Area into y bar square. Area into y bar square. What is y bar square? The distance away from neutral axis, right? Area is that area away from neutral axis. Suppose in this case, now area, this is neutral axis, area is here, right? So this is contributing in distance square times. Imagine a solid like this, and you have got area here. So what is use of the area into y bar square? So less. So I should have a area much away from neutral axis, which can contribute my lot of moment of inertia. This kind of column called efficient column, right? That is why nowadays Tata has brought out a new sections called pipe sections, hollow sections, hollow sections. Hollow sections could be circular or square or rectangular, anything, but it is hollow, with the concept that these kind of hollow sections are efficient. Now you may ask, among this C and D, which is a more efficient? Among C and D, which is a more efficient? So if you look at the C and look at D, now for the same area, suppose let us say this also having A, this also having cross section area A. Now which is more efficient? Obviously this is more efficient. Now if you make it rectangle, see lot of area away from CG is not here, available here, right? But whereas in the square, lot of area away from CG is available more to me. So among the hollow also, among the hollow sections, right? So the square, that right, hollow, square or rectangle sections are efficient. Of course, for the purpose of column, rectangles are no meaning, I can use hollow, square, right? For a beams I can use hollow, rectangles also better, okay, because generally for beams depth and width will not be same, not necessary to be same, right? So this is what I wanted to drive, so I have completed. So what I do, I will try to solve a simple problem. Wherein you understand the concept of how to use this Euler's theorem. Let us say determine, question is like this: determine the largest axial load, determine the largest axial load it can support, axial load which can support before it either begins to buckle or yield, before it buckles or yield. Remember that this material is steel material. Okay. So this is a question. Now I need to work out what will be my the axial load. That means he is asking to find out a P, right? Means find PCR or P, which is greater, which is maximum this column can. So I have not given details of column. So columns something said like this: there is I section column, which is connected with a pin at the bottom, and here also there is horizontal member like this fixed this side, and this also connected with the bolt, and the load is applied. So load is applied. So basically the section is ISMB. So this section here, the column section is ISMB, ISMB 100, that means depth is 100, and area of the cross section of this section is your 14.6 centimeter square. Try to understand the data, and Ix equal to 257 centimeter per 4 and Iy equal to 41 centimeter 4. This itself you can understand. So, if I take a cross section of this particular section, it looks like this. You think clear, right? So, this distance is my 100, right. So, if I look at carefully, this will be my y, this will be your x axis, y axis. I can put any way I want. Do not think that it is horizontally x and vertical y, it is not universal. Okay. I can draw any way I want. Okay. So, try to understand. Now, this is the data given to you, right, and it is steel member. Obviously, by looking at, now I am trying to solve the problem. So, obviously, looking at a problem, what we can understand. So, Ix is more than the Iy, right. So, because Ix is 257 centimeter per 4, Iy is 41 centimeter per 4. So, definitely Iy is lesser, that means Ix is more. So, which direction is going to buckle? So, buckle in the y direction, because y is weak axis. So, weak axis is going to buckle, that is very very important to understand, right. So, if you understand this, now let us try to solve. I mean, right now it is largest, try to understand what he is asking, largest axial load. Is it going to be yielding first or buckling? I do not know. Suppose it is going to yield first, I cannot use pi square E by L square. If it is going to be not yielding first, then pi square E by L square is going to be valid. Please understand this, you cannot get confused, you cannot just use pi square E by L square. So, what you do, let us first of all find out, because we know steel means your sigma sigma y is nothing but your sigma y is 250, right. Wait a minute. Okay, so sigma y I need to find out. So, sigma y is equal to P by area of cross section. So, load I do not know, right. So, now let us try to get, but I know that yield stress for the steel is given, means it is 250 Newton per millimeter square. Okay. So, let us get for this what is the stress, right. So, let us get the sigma PCR is pi square E I by L square. So, pi square E is nothing but 2 into 10 power 5 Newton per millimeter square, and I is the moment of inertia. So, which moment of inertia I have to use, Ix or Iy? I have to use Iy, because that is the least one. So, 41 into 10 power 4, I am converting into centimeter power 4 to millimeter power 4. Everything I want to keep in terms of Newton per millimeter square. So, L is your length of the column is given as 4 meter. Length of the column given as 4 meter. There is another data. So, this is your 4 meter, that means 4000 millimeter whole square. So, if I solve this, so I am going to get the P is to be 50 point or Newton 50,581 Newton, that is the load I am getting. Now, if I try to get sigma CR, which is nothing but PCR by A, area of cross section, which is 50,581 divided by area of cross section I know, which is 14.6 in the centimeter square multiplied by 10 square, which is millimeter square. So, I get is to be 34.64, right, 34.64 Newton per millimeter square. So, now it is clear to me that my stress sigma CR is much less than sigma y, right, because sigma y is your 250 Newton per millimeter square. That means, my buckling is going to be fast, yielding will be much later. Yielding capacity is 250 and buckling capacity only 34. So, now it means the load carrying capacity, the maximum load carrying capacity as per the question. What is the question asked? Question asked the largest axial load can carry, the largest axial load it can carry is equal to PCR. This is equal to your 50,000, that means 50.581 kilonewton I can write, convert into Newton to kilonewton, that is all. Please you have to verify your stress level. If at all this stress level is less than 250, then your buckling takes place. If your PCR is more than yield stress, then yielding takes place. So, you have to write corresponding to yield stress. That my point is only that, suppose the slenderness ratio of the column is very less. So, PCR is very high. PCR very high means sigma shear is very high, which will more than 250. Is it possible? No. I'll just okay. This is question complete. Now, I'll give you a hypothetical situation. Let us say PCR is equal to, let us say PCR equal to, let us say 1000 kilonewton, let us say 1000 kilonewton. So, sigma CR will be 1000 into 10 power 3 by, let us say 14.6 into 10 power of 10 to the power of 2. So, now if I try to solve this, what I am going to get? So, 1000 exponential 3 divided by 1460, what I am getting? 685. So, what I am going to get? 685 Newton per millimeter square, right. Now, this sigma shear is 685 millimeter square, but what is my steel stress? It is only 250, sorry, Newton per millimeter square. That means, my yielding is going to be early. So, my stress is more than yielding. So, definitely my column will not buckle first, yield first. When column yield first, my stress supposed to be sigma y equal to P by A, right, P by A. That means, my P capacity will be sigma y into A, which is 250 into area of cross section, which is 1460, equal to how much? 250 Newton per millimeter square into 1460 is equal to 365,000, right, thousands, right. That means, this is in Newton. maybe 365.00 kilo Newton. Try to understand. Actually, PCR is coming to be at 1000 kilonewton, but my yielding as per yielding, my load, which is your P load, is only 365. Means the column will yield crush at 365 only. What are you talking about 1000 kilonewton, right? So, that means my column going to fail first by yielding, not by buckling. So, if you write answer of 1000 by P square A by L square some formula, pi square A by L square, you are going to get a wrong result. So, never ever do that kind of mistakes. If material is given to you, yield stress is given to you, first verify. Just like our applied mechanics, the stress strain curve is given to you, you find out whether the stress is proportional to strain or not, right? If the proportional limit is there or not, you will find out. If proportional limit is not there, you cannot use stress by strain. Young's modulus cannot be used the same thing, right? So, that is a trick here, you need to verify. Okay. So, now I have got some more problem to be solved, but I am not going to do now because the time constraint. So, I will write down and send you some questions, and you all if you can solve for the, if somebody not able to understand the problem. So, you can see my video, I will send the link also, that will be in YouTube, you can see that link. Okay. So, now I will proceed further. So, what I do, let us try to solve. I mean, in reality what we have done is, the first case was both end hinge, right, both end hinge column, where I said the PCR is equal to pi square E I by L square, right. Now, what if the column has both ends, I mean one end fixed and other end free? Free is possible. Suppose if you look at it, a water tank standing on, I mean a single column or two columns together, right. So, the bottom you have got lot of foundation, you may do dry the pilings. So, you made it fixed, the top is free, you have put a load, axial load P is there, right. The axial load P is there, water tank model P is there, but it has got ability to free. So, something like this I draw here, right. The column is fixed at here, but you have got huge tank here, right. Tank has load P, right, the weight P. Now, due to this the column may buckle. So, the buckling will be unlike what we discussed the both end hinge, it will be buckling will be something like this, right. It go like this, right. It is not going to be like this, because that this kind of phenomena only when you put a hinge at the top. Now, it has got freedom to move like this lateral direction. So, what will be the load carrying capacity of such a tank, such a column, right? That is what we are going to discuss now. Please pay attention. So, derivation of the PCR now, PCR for one end is fixed, other end is a free. So, right. So, what we do, we try to get this column, applied load is your P, and right. So, let us assume the delta is a displacement, the column took place laterally, right. So, let us say this is a point A and this is point B, bottom point B, right. So, you understand, right. So, there is no rotation here, because fixed column or fixed beam, cantilever beam, it is like a cantilever beam only. If you look at make it horizontal like sorry, if you look at the column to be horizontal like this, and due to this axial load P, so it is going to be something like this, right. So, it is cantilever beam only. So, what happens? So, this is going to be, because free, it is going to deform. So, now at a distance x from fixed end somewhere, what will be my bending moment here? So, there is a deformation here. Let us say the deformation at x distance is y. So, what we can write, the bending equation E I d square y by dx square is equal to, right, the moment is nothing but the p into delta minus y, is it not, right? So, total deformation is your delta. At this point I have already deformation is equal to your y. The bending moment at this point will be due to this, right, this much deformation, that is nothing but your delta minus y. So, this much portion is bent because of the addition in the load. So, the deformation is your delta minus y. So, at distance x, right. So, delta minus y, sorry, not y, x. So, delta minus y is a movement, right. So, this is nothing but our movement at a section x from the fixed end. Now, simple. So, same thing, right. So, now I got a differential equation E I d square y by dx square. Let us take variable terms one side and constant term another side, minus plus p y again by that is all equal to p into delta. So, I can write this in the form of d square y by dx square, d square y by dx square plus p by E I y equal to p into delta by E I. Now, try to understand the differential equation which was not like earlier case both and hinge. So, I have a constant term also apart from variable, differential equation of two orders, second order, a single order, I mean not even single, simple variable and constant term also. So, this called non-homogeneous differential equation, right, non-homogeneous. Homogeneous equation because of the non-zero term on the right hand side. So, the solution for this will have a both complementary as well as particular solution. Please pay attention this. This is very important. This is part of mathematics because of the constant terms, non-homogeneous terms. So, I will have the complementary and particular form of the solution. So, the solution will be, the assumed solution will be y equal to C1 times sine of root over p by E I of x plus C2 times cos of root over p by E I x plus delta. This is what the solution meaning. Okay. So, now the only thing is I do not know the terms, coefficient terms C1, C2. The C1 and C2 is obtained from boundary conditions, So, what are the boundary conditions? Simply at x equal 0 at the fixed end, at one boundary condition is at x equal to 0 at x is equal to 0 and y is equal to 0, like displacement is at x is equal to 0 is 0, right. Now, if we apply this into this equation, so y becomes equal to 0, put into this equation here. So, what do we get? What we get is equal to x equal to 0 means this first term will be 0, sin 0 0. So, cos term will be cos 0 1. So, what we get equal to C2 into 1 plus delta. So, this implies C2 will be your minus delta. Now, if you substitute at second boundary condition, that means what is second boundary condition? So, for a cantilever beam, what is the slope at x equal to 0? At this point, what is slope? 0, right? Slope at fixed end, is 0. That means what is slope? Dy by dx. So, dy by dx at x equal to 0 is 0. So, let us try to find out the dy by dx for this. Dy by dx for this. If differential, right. So, differentiation of this term with respect to x. So, the dy by dx and then substitute x equal to 0. So, dy by dx is equal to c1 into root p by ei, right, cos of root p by ei x plus, but actually I have to give, because the cos is here is a cos term, cos differentiation is minus. So, I take minus c2 root p by ei sin of root p by ei x, right, delta differentiation is 0. Now, substituting x equal 0, right, x equal 0 means what? Sin this term becomes 0. So, what is left? Only c1 term, right. That means, slope is also 0, 0 equal to c1 times root p by ei, cos 0 is 1, right, cos 0 is 1. So, now the question is, right, this indicating that definitely load cannot be 0, material Young's modulus cannot be 0 and I cannot be 0, means second term is not 0. So, definitely what happens, not equal to 0, not equal to 0, definitely c1 must be equal to 0. You understand this point? Either c1 must be 0, whatever in the roots must be 0. Since second term is not 0, c1 will be equal to 0. That is very important. So, now try to get the deflection of this curve. Put it back c1 and c2 values in the equation what we got, that is y, the deflection, right, deflection, right. Go back, I just want to show you there, here this equation, here this equation, right, manaki enta c1 0 ochindi. So, first term is not there anyway, c2 enta ochindi manaki c2 minus delta, right. So, this is delta, right. So, using the same equation back, so what I am going to get is delta common teeste emostundi 1 minus cos root p by ei times x. So, right now, since the deflection is maximum at x is equal to L or at x is equal to L, how much is the y? Is delta? Is it not? I told you, right, the maximum deflection here was delta, because this was fixed. So, now substituting this here, so what I am going to get? So, delta equal to delta minus delta times cos root p e by I into L, right, right, this get cancelled, right. So, what I am going to get here is delta times cos root of p by e I into L is equal to 0. Now, again every time we are getting into the trivial solution, either delta equal to 0 or cos of this term, cos of this is equal to 0, right, which is 0. So, now let us see, if delta is equal to 0, for example, say delta is equal to 0 means what? The column delta equal to 0 means this is not there, that means your column is straight, that means there is no buckling. How is possible? When you apply, go on applying load, do you think that the column will not buckle at all, will not go lateral deflection? Not possible, right. So, based on this, that means column is straight, delta equal to 0 means column is straight. So, which is not possible, right. So, it is not possible. So, because it is not possible, we have the delta is not equal to 0. So, since delta is equal to not 0, then cos of root p by E I into L is equal to 0. Okay. So, I have to say this is not 0. So, other one is 0. So, then I have to get the solution, right. At what values of this theta cos is 0, that is n pi by 2, right. Square root of p by E I into L equal to n pi by 2, assuming the least mode, the first number is n is equal to 1, right, n is equal to 1. So, then squaring both sides, what I am going to get, p equal to or PCR equal to critical time pi square E I by 4 L square, pi square E I by 4 L square. This is why critical load carrying capacity. Now, this is both one end fixed and another is free, fixed and free, but both end hinge. I got PCR is equal to pi square E I by L square. Now, can you understand how much load carrying capacity reduced because of the one end free? It is 4 times reduced, 1/4 directly. The column carrying capacity is reduced to 4 times. That is why we try to not allow the one of the end to be free. That is why we allow a column one of the end to be free. Free means always risky, is load carrying capacity going to reduce. Okay. So, thank you. So, remaining we will see in the next class. And what I am going to do, so I am not going to explain the load carrying capacity for another end. We may have like one end, let us say third case is both end fixed, both end fixed. Second case is one end fixed, other end is your hinge. So, all 4 cases we can discuss the PCR. So, these 2 things you can try to practice. So, I will send a video, so you can practice from that and send the assignment. You have to send me the assignment for that. You have to solve it. You can take help of my video and the 2 problems which I am going to explain for the first concept of both and hinge. Okay. So, for this both, so then we go for the effective length concept. Okay. Thank you.